Okay, hi everyone. Thanks a lot for the introduction, Rong, and thanks for the invitation to be here. It's great to be here at workshop number 4. Yeah, I'll be talking today about principal components along Quiver representations, and this is all based on joint work with Vidit, Nanda, and Heather Harrington, who are some colleagues of mine in Oxford. All right, so before I dive into Quiver representations, I'll start with something which is maybe a bit more familiar to the long program and to the workshop. So I would like to consider a tensor of data, and I will draw it like this. So what do I mean? Well, each row is a sample. So let's say I have n rows. Each of these rows correspond to one sample, and each column is a measurement. So here there are 20 different measurements. So that's the number of columns. But the measurements are not all unrelated. They're organized into blocks, which are here represented by colors or by these curly brackets at the top here. And this is some sort of block type organization of the different measurements that I or someone else has taken. So for example, each block could correspond to a different time point, and we've taken the same set of measurements, but across different time points. Or each block in the context of some biological data could correspond to a different biological tissue, so a different setting in which to take the measurements. So that's sort of thinking in the context of this GTEx project down here. Or the blocks could be something else, or some other experimental condition which is varied from one block to another, but where we have the same measurements in each of the blocks. Okay, and then we can think of this data instead of in this flattened form with the blocks of different colors. We can think of each color or each block as being a slice of a tensor. So here's the corresponding tensor here. So each entry of the tensor is some data measurement, and here, let's see, we've still got n samples, and we have 5 measurements across 4 different blocks. So this is an n by 5 by 4 tensor. Okay, so a sort of motivating question for what I'll be talking about today is what should we do if the columns are not aligned? So if our measurements are aligned in this tensor slices kind of way, then we know that there's lots of tensor algorithms and tools that we can use to find structure in this data, and that we hope are helpful and informative for a particular application. But how does this extend to the setting where the columns of the tensor are not aligned in this nice way, where we have blocks all of equal sizes, or the sizes all line up? So, okay, here's a picture of a different data set where many things are still the same. The rows are still the samples. Each column I want to think of as a measurement. The measurements are still organized into blocks, but we can't really think of these as the slices of a tensor. I mean, we could pad each index and sort of force it to be a tensor, but we don't have this nice alignment along each of the measurements. So it's not necessarily the case that the first measurement here corresponds to the first measurement here, and so on. So what should we do in this case? All right, so here are our blocks of measurements of different sizes, and I want to index the blocks by some index which I'll call V, which lives in big V. So here the number of different blocks is 7, and then each sample is a vector yi, but I want to split it into yiv, which is the part of the vector that lives in the block V. So I've got the first yiv is here, and then the second part, and the third part, and so on. And yeah, as we saw before, the blocks are not aligned. Okay, then I can think about assigning to each block a vector space, which is the vector space in which the measurements in that block live. So if I take the first block, this red block here, or the block corresponding to this curly bracket up here, then each measurement lives in the vector space R5 in this block. So I attach the vector space R5 to this block, and then there's 4 measurements in the second block here. So I attach the vector space R4, and there's 1 measurement in this small green block here, and so on. Okay, and the blocks are not aligned, but they may still be related. So if they were completely different measurements, it wouldn't necessarily make sense to group them into blocks like this. But as in the original tensor case that I mentioned, the blocks still have some relations between them. So maybe we can think of these relations as being given by maps, which take us from the set of measurements in one block to the set of measurements in a different block. And we can make an assumption that the blocks are related not just under any old maps, but under linear maps. So here, these arrows represent the maps that take us from one block of measurements to another. And if they're linear maps, then, okay, here are some little cartoon pictures of linear maps that are represented by some matrices of a correct sizes. For instance, the map from R5 to R4 is this 4x5 matrix. Okay, and all this is to say that the connections between the different blocks of measurements in this case give us a Quiver representation. Okay, so what's a Quiver representation? Well, firstly, what's a quiver? So a quiver has a set of vertices given by some vertex set V, and a set of edges or arrows given by a set E. And we allow loops and double arrows along between a given pair of vertices. But apart from that, it's just a directed graph, like this one here from the previous slide. Okay, and then a representation of the quiver assigns vector spaces to the vertices. So each vertex gets a vector space, and it assigns linear maps to the edges. So here are the assignments of the vector spaces. So there are the vertices, the vector spaces attached to the vertices, and then the linear maps on the edges. And to sort of set up the notation, more specifically, we can call the representation A, and it assigns to each vertex V a vector space, which we'll call AV. And to an edge E that goes from node U to node V, it assigns a linear map, which I'll call AE, which goes from AU, the vector space at U, to AV.
Sorry, so there's a question from Edina Coffee now. So the question is the all degree of every vertex in the quiver always equal to 1?
No, it's in principle we can have any okay, thanks for the question. No, in principle we can have any out degree or in degree of any vertices. So I was just looking at this example. Hopefully not every vertex has out degree 1. Yeah, I think this vertex here we've got 2 arrows going out. But yeah, any pattern of arrows is allowed. This is not the best choice of a sort of generic type quiver. We'll see a better choice a bit later. Thanks for the question. Are there any other questions? Okay, great. So yeah, here is the notation for the Quiver representation. And let's go back to the example of a tensor of data to see how all of this might specialize to that case. So before we had this sort of block structured data measurements that we could think of as being the slices of a tensor, we can instead think of them as being data measurements taken with respect to some quiver. For example, this one here. So we have a vertex for each block. So we've got 4 vertices, and then maybe we have linear maps going from the first block to the second, second to third, third to fourth. For example, if these are 4 ordered time points, then maybe this is an appropriate way to structure this data. Okay, and then our quiver representation assigns a vector space to each vertex, and the vector space for all 4 vertices is R5 because we've got 5 measurements in each block, or each block has 5 columns in it. And now let's imagine that we have some linear maps on the edges. So this tells us how these 5 measurements transform to give these 5 measurements, and how these transform to these, and so on. And as before, each row is a sample. And we can assume that the maps are given by scalar multiplications. So then this first map is just multiplication by lambda1. So lambda1 times I5, the 5 by 5 identity matrix, and so on. And say we want to find the best rank 1 approximation of each block. Okay, so this would then be finding the best rank 1 approximation of 4 different matrices, which we can do. But we want to impose that each of these rank 1 approximations are compatible under these linear maps. So under the maps that are assigned to the edges of the quiver. So if we impose that, then our best rank 1 approximation will take this form. So let's say that A tensor B is the best rank 1 approximation of the first block, subject to this compatibility. Then the best rank 1 approximation of the second block has to be obtained from the first one by multiplying by lambda1. And then, okay, this is a typo. There should be lambda2 times lambda1. So to get the third block from the second block, we want to multiply by lambda2. And this is another typo, which now looks suspiciously like a mistake rather than a typo. To get the fourth block from the third one, we would want to multiply this one by lambda3. So here, this should be lambda1 times lambda2 times lambda3. Okay, and so we can recognize that this decomposition has a particular structure. So this is writing, thinking back to the measurements as being from the slices of our tensor. This is writing our tensor in the form A tensor B tensor C, where C is this particular vector whose entries come from these linear maps, but not like this. So C has entries 1, lambda1, lambda1, lambda2, and lambda1, lambda2, lambda3. So there we can see the connection between rank 1 approximation of a tensor and this idea of finding approximations of our measurements subject to compatibility under the linear maps given by the quiver representation. And it's this part that I'd like to talk more about now, this idea of looking at low rank structure that's compatible under these prescribed linear maps. Okay, and finding a low rank approximation subject to compatibility under linear maps is an optimization problem over the space of sections of the quiver representation. Okay, so what's before we get to the space of sections, let's recall that our quiver is given by vertex set V and edge set E, and this is our representation A. So it assigns the vector space AV to each vertex V and the linear map AE to each edge E. Then a section of the representation is an assignment of one vector in each vector space. So a vector in each vertex of the quiver, but not just any assignment of vectors. We want one that's compatible with all the linear maps on all of the edges. So for each edge E that goes from U to V, so for example, let's say this is U and this is V, then I have my section restricted to this vector space, which is gamma U, and the section restricted to this vector space, which is gamma V. And I want it to be the case that when I apply the linear map on the edge to gamma U, I get gamma V. So I can move the section around the quiver under the maps given by the representation, and I'll always get the part of the section that was in that next vertex. Okay, and I'll denote the set of sections by this gamma QA, sort of sheaf-like notation. And this is a subspace of the space of all possible tuples of vectors, one in each of the vector spaces at the vertices. Okay, so maybe the first example of a section is to just assign the vector 0 at each vector space. So these are all linear maps, so they all set 0 to 0. So if I just say that I have a vertex, I have the vector 0 at each vertex, so in each vector space, then this is a valid section, but we're looking for sections that are a bit more interesting than the all zeros one. And our first goal here is to describe the space of sections of the quiver, because when looking for compatibility on the linear maps, this is really saying that we're working in the space of sections, because provided we stay in the space of sections, we have this compatibility, and once we leave, we no longer have it. So we want to consider some sort of low rank approximation that's constrained to be within the space of sections of the quiver representation. Okay, so let's see some examples of some quivers and representations, and then the space of sections that we get. So I'll start with some rooted examples. So firstly, let's consider a path. So like the quiver that we saw before with the tensor, we have some nodes in a line with arrows between them. And the space of sections here is just isomorphic to the vector space that's assigned to the first vertex, which I'll call the root of the path, since every it's a root because it has a path to every other vertex, a directed path to every other vertex in the quiver. So why is the space of sections isomorphic to this first vector space? Well, for any choice here, you could just sort of percolate it down to get a section across the whole quiver. And then, conversely, if you have any section, it's determined by whatever value it takes in this first vector space here. So for a path, this question of determining the space of sections is not so difficult. You just look at the first vector space. And this also holds more generally. So the space of sections will be isomorphic to the vector space at the root. For any quiver that has a root and that has a unique path from that root to every other vertex, just by sort of repeating the same argument here, that we start with the root and then we percolate our section to get to whatever vertex we are interested in. Okay, so such a quiver that has this property that it has a root and a unique path from that root to every other vertex is called, or one name for such quivers is an arborescence, and that's the name that I'll be using here. And the idea is to take some very complicated quiver and to reduce it to a quiver that has this property in such a way as to preserve the space of sections. Okay, but not all the examples are so direct because we don't always have a root with this property. So let's see some other small examples and what we get for the space of sections. Okay, well, maybe the smallest example is just a single loop. So we have one vertex, let's say it's V, and then the loop is E. So the space of sections is what? Well, it's the vectors in the vector space over the vertex, which when you apply the linear map attached to the loop are invariant. They don't move at all. You get back the same vector that you started with. So it's the subspace of AB that is fixed by the map AE. So it's the eigenspace of the map that corresponds to eigenvalue 1. All right, and another example. So here's the Kronecker quiver with 2 arrows. So we have 2 vertices, let's say U and V, and 2 edges, E and F. Now, what is the space of sections? Well, each section will be an assignment of a vector to this vertex and a vector to this vertex, such that when we apply the one linear map or the other linear map, we get to the first vector, we get the second vector. So AE applied to gamma U gives gamma V, and likewise AF applied to gamma U equals gamma V. Okay, and this means that gamma U, so the section of this first vertex here, has to be in the kernel of the difference between these two linear maps. Okay, so, and this is the only condition that characterizes when something is a section or not. So the space of sections is just isomorphic to the equalizer of these two maps, or the kernel of the difference between the maps. Okay, and then if these types of structures, so if a loop or if this Kronecker quiver occurs as a sub-quiver of some larger quiver, then we would want to apply these kinds of arguments to restrict the space of sections of the overall quiver by imposing the restriction of that sub-quiver. Okay, so we want to sort of scale this up to deal with a more general quiver. So what's a principle that holds? Well, if P is a path in Q, so we start at some vertex U and we apply a sequence of directed edges to get to some vertex V, then the representation assigns linear maps to edges, but also assigns linear maps to paths just by composing the linear maps along the path. So we can assign to the path P the linear map, which I'll call AP, which first applies the linear map corresponding to the first edge, then the second edge, and so on, and then the kth edge. So it applies the linear maps along this sequence. And if we have any two paths, P and Q, from a vertex U to a vertex V in the quiver, then our section gamma must have this property that regardless of whether we apply the linear map AP or the linear map AQ, we have to get the same answer when applied to the section at U. So this says that gamma U has to be in the kernel of the difference between these two paths. Okay, and this generalizes the previous two examples. So in the loop, we have sort of a trivial path where we have that the section is in the kernel of some matrix minus the identity. And in the second example, of the conical quiver, the paths were just individual or single edges. Okay, so now our goal is to describe the space of sections so as to do some optimization problems over it. And I mentioned before that the idea of how to do this is to apply a sequence of restrictions to the quiver that simplify the quiver to an arborescence, which is much easier to find the space of sections for, but that don't change the space of sections. So now I'll tell you what this sequence of restrictions is. So let's take this quiver here, and we can see that as subquivers, it has the examples I was talking about before. So we've got a loop over here, and we've got a conical quiver with 2 arrows here. And yeah, we want to find the collections of vectors, 1 vector for each vertex, that are compatible under some fixed linear maps. So the linear maps assigned to the edges. And this will be some vector subspace of the vector space given by just the product of these different vertices. Okay, so the first step is to remove the cycles in the quiver to get what we call the acyclic reduction, denoted Q star. And along with this reduction, okay, so here's the acyclic reduction of the quiver. So the cycles were all occurring over here, or this loop was also a cycle in the original quiver. So we have a way to remove these cycles. So this is our Q star, our acyclic reduction. And it comes with a quiver representation, which we call the acyclification, and is denoted by A star. Okay, so that's well, step 2. Step 3 is to add a new initial vertex R, which will be our root. So here's the acyclic reduction, but if you look here, there are 2 vertices that have no incoming arrows. So this vertex here has no incoming arrows, and also this one has no incoming arrows. So we want to have just a single root, like we had in these easier examples. So we can just introduce a root. So this is our new root appearing here. And
sorry to interrupt, 5 minutes left.
Okay, thanks. And we'll call this the augmented quiver Q plus, and it has this new vertex R as a root. Okay, and now we have a new representation, which we call the arboreal replacement. So this is a representation on not this whole augmented quiver, but on the spanning arborescence of it. So the rule for being an arborescence is you have to have a unique path from the root to any vertex. And here we almost have a unique path, but for example, if we consider a path from the root here to this vertex here, then we have 2 choices, because we can either go along this arrow or along this arrow. So we want to, and then similarly to get here, we can either continue along there or continue along there. So we want to get rid of these different choices of paths that we can take. And we can do this by restricting to an arborescence that spans the overall quiver, i.e. that reaches every vertex. Okay, and here's our choice of arborescence to take. Okay, so yeah, in the paper we describe a recipe for doing each of these steps on a general input quiver. And then the theorem that we're looking for is that none of these changes affect the space of sections, or rather that each of these changes have been done so as to preserve the space of sections. So now we have this sequence of progressively easier quivers to compute the sections for. So we started with our complicated quiver, and its space of sections. We turned it into an acyclic quiver with its sections, and then to a arborescence with its sections. And finally, we know that for an arborescence, it's the space of sections is just the vector space that's assigned to the first vertex here. Okay, so I wanted to tell you more about the approach that we take to compute the acyclic reduction and the acyclification, which we approached using the ear decomposition of a strongly connected quiver. But maybe in the interest of time, I'll skip this unless there are any questions, or maybe in the discussions afterwards. And instead, I will go back to the original motivation for constructing this space of sections, which is the idea of computing low-rank approximations that respect these linear maps between our different blocks of measurements. So in this final slide, I'll describe what it means to compute principal components in this setting. So the input to doing principal component analysis is to take some mean-centered data. So let's say I have n samples in Rn. Okay, and then the sample covariance matrix is what I'll use to compute the principal components. So this is S, the sum of the outer products of the sample vectors averaged. So in usual principal component analysis, the idea is to project our data, which lives in some high dimensional space, so n is assumed to be quite large, to some lower dimensional space. Let's say it's r dimensional. And this projection should be orthogonal. So it's given by a matrix X of size n by r, and the r columns should be orthogonal and are chosen to maximize this, this trace. So we want to maximize the trace of X transpose Sx. But now we want to restrict the principal components to lie in the space of sections. So the space of sections is given as the image of a linear map. So this is our root vertex that we ended up with after this sequence of restrictions. And it gets mapped into the full possible vector space in which the sections could lie. And since everything here is a real vector space, it's given by some real matrix F. Okay, so F is a full rank real matrix. And to find principal components along the quiver representation, we want to do some optimization that's not over the whole space, but rather that's over the image of this map F that parameterizes the space of sections. And yeah, I'll conclude with a theorem that describes these principal components. So the rth principal component along the quiver representation is spanned by FUR, where UR is the eigenvector of the matrix pencil F transpose SF minus lambda F transpose F. And it's the eigenvector corresponding to the rth largest eigenvalue. So we can see that it's both the covariance matrix S, but also the map parameterizing the sections that plays a role in determining the different principal components here. All right, and yeah, that's the paper if you want to see any more details, and thanks a lot for listening.